So today, that's the penultimate lecture. I'm going to finish to discuss the issue of gauge fixing in non-abelian theory and look at the form of the gauge fix action we obtain after the performing gauge fixing conditions so that we can perform perturbation theory and start to discuss, hopefully, a bit of the physics of non-abelian gauge theory. So first, I'm going to, so remember what we did. Well, we defined a functional integral, but we have this problem of redundancy of, due to the gauge, the huge gauge invariance of the action. And therefore, we need to use the gauge fixing. So remember, first, we had a trick. So we had a big functional integral. Let me write it like this one. A exponential of minus, well, let me write it well, this is an exponential. I'm in, let me stay in Minkowski space. So this is the measure on the gauge potential, and this is a Yang-Mills action, which is invariant to the gauge transformation. Okay? So let me call this Z. That's standard notation. You can imagine that you had a source term to generate the correlation function of your theory. And the problem is that both the measure and Yang-Mills are gauge invariant. And gauge invariance means that when we transform a gauge potential configuration into a gauge potential configuration AG, where G denotes a gauge, a local gauge transformation, then this doesn't change and the measure doesn't change. Okay. And so A belongs to the set of gauge potential configuration, and G is an element of the gauge group. So A belongs to what I denoted curly A, and G belongs to curly capital G, which is the gauge group. And this is the space of gauge potentials. Okay. And we had this picture that I drew yesterday that, well, let me write it here, that we have the space of gauge potential. Given a gauge potential, you have an orbit of the gauge group, and we integrate over this whole space, but a lot of configuration describes the same physical configuration. So we fix a gauge slice through a gauge fixing condition. So we introduce the gauge fixing condition. That I use in a very sketchy way, f of A equals 0, which isolate a gauge slice. And hopefully, we hope that the gauge slice is transverse to the orbits. First condition. And second condition, that there is only a unique intersection. And that's a subtle point. Okay. So this means that given an A, we hope that there is a unique G that I'm going to call GF of A. So A belongs to the space of gauge potentials. There is a unique gauge transformation, so an element of the gauge of the big gauge group, such that f of A, of gf of A equals 0. Okay, that's a bit heavy notation, but it means simply that this is the original A, and this is the transform A, which belongs to the slice. Okay? And we want to transform this big integral into an integral over the gauge slice. Okay. So this is a gauge fixing condition. Now, so this is the point, first point. So in order to transform the integral over A into an integral over the gauge slice, I said that there is a trick, trick 1, which amounts to insert in this path integral 1, write 1 as an integral over the gauge group of d mu of g, where this is the R measure. So the measure invariant under gauge transformation itself of a big delta function, which is a delta function of g minus gf of A. So for each A, I'm going to insert 1, but I write 1 in this involved way. It's an integral over the gauge group, over all gauge transformation, but I keep only the gauge transformation such that A is mapped to the gauge slice. Okay? And now we have seen from the general property of integration of a delta function that since g of f, gf of A is defined by this condition, we can rewrite this as an integral over g of d mu of g times delta of f of A of g. Okay? Because that's, okay, so this is a very compact notation, but of course, what we have to do is when we make this change of variable in the argument of the delta function, we have to take into account the Jacobian of the change of variable. And the Jacobian of the change of variable writes in a very sketchy way f prime, which is df over dg. So this is let's say this is the absolute value of the determinant of the operator df over dg, where df of A of g, of course, divided by dg. Okay? And I gave on the example of a simple D group what this is, but remember, this is a big operator. This is a Jacobian operator. So this is a functional determinant, it turns out. But I'm going to write it. And so this is the absolute value of the determinant of this object. Okay. So now, okay, so that's compact notation, but okay, so now we insert this into A. So we can write this as integral over dA, exponential integral over dg, etc. This. Then we can invert. So we invert the integral by writing z as integral over the gauge group, d mu of g, integral over the space of gauge potential dA. We have our exponentials, which doesn't S Young-Mills of A. And then we have this determinant, absolute value of the determinant of df of A of G with respect to variation of dg times delta of f of A of G. Okay, so gauge transform. Okay. I'm just. And now we can use the fact that the measure and the quantum phase factor are invariant under gauge transformation. And since now I first integrate of A and then in G, by making a change of variable, I perform a change of variables, where in this integral here, as variable of integration, instead of using A, I use AG. Okay. Of A. I'm using this integral, so G is fixed. You see. And if I do this integral, I end up with Z equal integral over G over d mu of G times integral over dA, d of A, exponential I, the action of A, equals same. And then the determinant of df, now it's f of A, which is G times, so this is going to be the same thing, but now I can consider that G is a small configuration, and f of A. Okay, so I make this derivative, but then I make a G equal identity. So I just make a gauge transformation in the vicinity of A. So let's say we can write this as dg over dt at A. So this is a function of A. Determinant, which is a function of A, and here I have delta of f of V. And so you see that the factor, which is the volume of the gauge group, factors out. So we can forget about it. It's just a normalization of the measure. And we end up with this gauge fixed functional integral. Functional integral. Okay? And, well, so we did the job. We transform the integral over the whole space of gauge configuration over an integral over this. Okay? And this is the measure we have to use on A. And you see that the fact that the measure contains a determinant of the derivative of the gauge function, gauge fixing function, means that the measure will be different locally over different slice, simply because we use a different system of coordinates. So the result is gauge invariant, but different, we have to use different measure if we use different gauge fixing conditions, because in some sense we are using a parametrization of a physical configuration by different sets of gauge configuration. Okay. So this term ensures that the final result is gauge invariant. Okay? Good. Okay, so this was trick 1. Now, there is a beautiful trick, which I'm going to call trick 2, which is due to Fadeev and Popov, which is to introduce ghost fields to represent the determinant. Okay? And this is a mathematical way to represent the determinant, which is useful for 2 reasons. First, it's useful in order to define, to put on the same footing the integration of A and the determinant in perturbation theory. And path and functional integral. So we are going to represent this determinant as another functional integral. But it's also useful in order to implement this gauge fixing condition in terms of canonical quantization and Hilbert space. So to describe what is the Hilbert space of a gauge fixed gauge series in a way which is consistent and simple representation. Okay. And from that point of view, the introduction of ghost field appears in other areas of high energy physics and theoretical physics, for instance, in string theory and conformal field theory. Okay, so, but I'm going to, okay, so the point is that we have a determinant here. So let's assume that the determinant doesn't shine along the gauge slice. And if the determinant, if this is the second condition, the fact that there is a unique intersection is valid, the determinant shouldn't vanish because it will vanish if something happened. Okay. So then we can replace the absolute value of the determinant by just the determinant. Okay. And we have seen that when I introduced on Monday gauge configuration, I'm sorry, path integral for fermions, we have seen that we integrate with Grassmann variables a quadratic form, exponential of a quadratic form. We get the determinant of the quadratic form. So we're going to use this trick. We are going to use the fact that we can write the determinant of this quadratic form. Well, let me call it G. The determinant of the Jacobian. So let me call this determinant G. So this is the Jacobian matrix df of A of G divided by G at G equal identity. So this is a functional determinant that's, well, that's a matrix. So that's an operator. So it's a Jacobian operator depending on A. Okay. We can write that the determinant of this Jacobian operator, G of A, we can write it as a fermionic path integral over 2 fields, a C bar and a C, exponential of, and I'm going to write this as I, the I is not important, C bar G C, where C is called the ghost field, and C bar is the anti-ghost. But they are something conjugate Grassmann fields. So they anti-commute. Okay. Okay. So now, with this trick, the determinant appears as an integral of a Grassmannian field of an exponential, so that adds up with the action. So the action is now the Yang-Mills action plus this action, which involves the ghost and anti-ghost. And remember, since G is going to depend on A, there is a coupling between the ghosts and the gauge fields. So it will change the action of the. Okay. And finally, if you like, trick 3, which is not going to play a very important role. But what you can do is that it's not a trick as deep as this one. You can write the delta function using a Lagrange multiplier, namely taking the Fourier transform of delta function by writing this as integral over d of lambda. So this is a lambda field, so not exponential of I lambda times f of a, where lambda is a Lagrange multiplier field, because lambda f of a, where f of a is a set of constraints, and so lambda is going to be a field depending on A and with color indices. Okay. And with that, you have a final action, a gauge fix action, which is of the form very schematic way. S Yang-Mills, so the S gauge fixed is S Yang-Mills of A plus or minus, the sign is not very important, C bar G of A C. Let me write them. No, let's put a plus lambda times f of A. Okay, so it depends on A, C, C bar, and lambda. Okay. And so lambda is a bosonic field. A is a bosonic field. So in fact, lambda is going to be a spin 0 field. A is going to be a spin 1 field. And C, and the problem is that C and C bar are going to be spin 0 field, but anti-commuting. Okay. So that's the trick. Okay, so now, of course, this is very, very schematic. So let me see what this gives for, and I'm going to do what this gives for the Feynman gauge. So the Feynman gauge, remember, is that d mu of A mu equal epsilon, where epsilon is chosen. Okay. So, and this means, in fact, in terms of coordinates, that d mu of A mu A of x equal epsilon A of x, where A are group indices that belongs to for the adjoint representation of SU2, because A belongs to adjoint representation of SU2. Mu are the Lorentz indices, and X belong to Minkowski space. So this is a space position. Okay. Okay. So with this choice, we must realize of what is the operator. What is G? What is G? Is this Feynman gauge? What is G? This very formal object. Okay. So now you remember F means that for each A and for each X, we have a gauge fixing condition, which reads like this one. Okay. And then we make, so this means that we change A into AG with G equal 1 plus alpha of X times, where alpha of X, this is the identity, and alpha of X is an infinitesimal element. There is an I, sorry, of the adjoint representation. So alpha of X is means alpha A of X TA. Okay. So when I write that G is dF of A of G divided by TG, this means that for each X and XA, I see how, so let's call it, so the Feynman gauge is this, so F is this. So this means that I can write that this is the gauge condition F A of X. Okay, so this is a set of gauge fixing conditions. So this means that what I am computing is how does Fa of X vary when I vary G by an alpha P of Y. Okay? And this is going to be G. So G is a matrix with color indices and is going to be a kernel in X and Y. So this is a kernel of G. Okay? So it's a 3-by-3 matrix whose elements are a kernel. But since, in fact, F depends on Y, simply since it has a differential operator, you can check that this kernel of G is a kernel of a differential operator. Okay? And you do the calculation by just writing what is the effect of an infinitesimal gauge transformation of a gauge field, and this is something that I discussed at length yesterday. So I just write the final result. This differential operator is just chop. This differential operator is d mu. So it's a derivative of the covariant derivative, which depend on A. Okay? This is the ordinary derivative. That's because here there is an ordinary derivative of A. And this is a covariant derivative. And it doesn't depend on epsilon because epsilon is a fixed function. chose the function. Okay. So this is d mu of d mu, and therefore, if you write it, so this operator is d mu of covariant derivative d mu, and therefore, remember, this is an operator that acts on an element in the adjoint representation. Yes?
So the product there is the composition of the two operators?
Pardon? Yes, it's a composition. It's d mu applied on d mu. So I'm going to write it in a differential operator. So this is just, in fact, if you want. And remember, d mu is just the ordinary derivative minus I times the commutator. So remember, d mu is just d mu minus I a mu commutator with this thing. So if I apply d mu to something, this is d mu of this thing minus I times the commutator. When applied to an element of the space in which G acts, which is an element of the adjoint representation of SU2. Okay, and therefore, in terms of component, GAB. So this is going to be a differential operator. I just omit x and y, and I write the corresponding differential operator, derivative operator. GAB is just delta AB times, well, I'm writing the operator. Now, let me write it GAB with the indices. No? So this is delta AB times the Laplacian operator, which is d mu times the ordinary derivative. Okay, this is standard Laplacian. And then there is a term that comes from applying d mu on this. And it's easy to compute because it involves the structure constant of the Lie algebra that defines the commutator, which for SU2 are epsilon ABC. Okay, so you get two terms. So you apply d mu either to a mu or to the object you apply. So you are going to have a term which is epsilon ABC. I think there is a mistake. There is a typo in my notes. So this is going a mu C times d mu. So I apply something here. So you see, I apply this to the function. This is Laplacian. This is the ordinary derivative applied to the function. And then there is a term which is just proportional to the multiplication by d mu of a mu C. Okay, so this is the function. Okay, so this is the ordinary Laplacian plus the gradient operation times a mu plus a term that involves the divergence of A, multiplication by the divergence of A. And that's because for SU2, the structure constants ABC equal to epsilon ABC. Otherwise, you are going to replace this by the structure constant of your Lie algebra. Okay, so this is GA. So you see, GA is an operator that involves derivative. So the action for the gauge field involves a Laplace operator. So they are going to propagate and to interact with a mu. So in some sense, C and C bar propagates, and interact with A. Okay. So Okay, so now we are done. Now we can write explicitly the ghost action as C applied to this. So the ghost action is, so it depends on C bar, and on A. And this is simply I'm going to write in terms of component. So this is dx. And remember, okay, now remember, the ghosts, in fact, are related to multiply C and CB. So the ghosts carry index of the adjoint representation. So the ghost leaves also C and C bar belongs to the adjoint representation, because they're associated to how you modify the gauge function, the gauge condition function that lives in the adjoint representation by variation of the gauge transformation that lives in the adjoint representation. Okay, so they carry indices A and B. And so finally, this is C bar of A delta AB. So let me write the ghost with an action. Yeah. So this is just the ordinary delta function minus delta times CB of X. So this is the ordinary delta function plus epsilon ABC. Then I have d mu of C bar A of X. Right, so you see, this is a derivative that acts to the left, to the right, and this is a derivative that acts to the left. So you can write this as the derivative acting to the left of A mu times something. And then you can integrate by parts. So I'm going to write this as a derivative acting, that's a term that is to the left instead of to the right. So this is d mu of C bar A. It just makes something simply times A mu B times C. And everything depends on X. You see, so this is relation with respect to X. Okay, so C means C A of X, and C bar, I denote it C B bar B of X. Okay. Yes?
Where does the overall minus come from?
Pardon?
So in the second one, you integrated by parts, still there's a plus, and in the first term, there's a minus. Where does the minus come from? Like you have G with plus, 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 and your action is stuff plus C bar JC.
That's because I write the action to be, that's because I wrote I, therefore there should be minus something here, I think. Well, it means that's possibly my signs are not completely consistent. Okay, so this is the final result, but there may be some typos, let's say. Okay, so just check. But I'm not going to make explicit calculations, so the important point is that the general form of the action. Okay? Okay. And one last point is that you see is that in f of A, well, no, before discussing the gauge constant term, you see that C and C bar are fermionic field, they're anti-commute, so they belongs to they obey Fermi-Dirac statistics. So this term is going to be to give a propagator for the ghost, and I'm going to write the ghost as dashed line because ghosts, so they are not real fields, physical fields. So I write something that the line goes from C to C bar. I use the same notation for Dirac fields. Okay, but of course then the propagator of a ghost is 1 over p squared in momentum space because here is associated minus delta. So the propagator preserves the color of the ghost. Okay. So this goes from CA to C bar A. So in some sense, it is, let's write it, this is times delta AB. Okay, so it preserves the color of the ghost charge, yes?
So that expression that we have for the determinant of J case,
Yes.
we just said that the ghost fields belong to the adjoint representation.
Yes.
Why cannot there be fields in the fundamental representation? Like from that exponential? Could I make
It cannot, because it's just a way to write a determinant of a matrix F or an operator F that carries index labeling the different component of the adjoint representation. The gauge fixing conditions are conditioned on the component of the gauge potential. And the gauge potential lives in the adjoint representation per se. And therefore, everything that's connected to gauge fixing, I have to, you have no choice. Okay. You could add a matter field in various representations, that's perfectly possible, but the ghost will still belong to the same representation that the gauge potential and the gauge field.
All right, so in that exponential, I would have exponential I times a matrix.
Yes.
In the adjoint representation.
Yes.
That's the determinant.
Yes.
Okay.
Okay, so the propagator for the ghost is this kind of thing. But you have this term, which is an interaction between the gauge field and C and the C bar. And if you use the same diagrammatic Feynman notation, you see that you have a ghost field. So if I represent the ghost field by, if I represent the gauge field A mu by a wavy line, as is done in QED, but remember that it carries an index P, you see? And here, if I have a ghost C with an index A, and then here an anti-ghost with an index C, so there is a vertex like in QED, but it carries a momentum here. So in fact, it carries a momentum of the outcoming anti-ghost field, ghost field. So the contribution of this is that you have an epsilon ABC that comes from the structure of the gauge group. And then you have a momentum P mu for this outgoing ghosts. So the coupling between the ghost and the gauge field is different from the coupling between a fermion and the ghost field. But that's because the propagator of the ghost field is 1 over p squared, while the propagator for fermions is 1 over p slash. Okay, so this is the interaction between ghosts and gauge field. Okay. Okay, so now finally we have to see how do we treat this lambda. So this lambda, in fact, is just the gauge fixing condition, so it will project out when you treat the quantization of the Yang-Mills. What did I SI? This is Yang and Mills. It will project out for d mu the longitudinal modes. But we can use, if we use the Feynman gauge, we can use, there is another trick which makes calculation. It's just a technical trick that makes calculation a bit more simpler. The idea is to replace in the gauge. So you see, the Jacobian doesn't depend on A, on epsilon. The gauge field doesn't depend on epsilon. Epsilon is just a parameter. So the idea is to replace in the gauge fixing condition by integrate over epsilon. Integrate over epsilon, which is a parameter in the gauge fixing condition. By integrating, by writing just by integrating like integral the epsilon exponential minus I over 2. I'm going to introduce a parameter chi. This is just a parameter. Okay, times epsilon squared. Okay, so in this picture, this means that since I know now exactly how to integrate over gauge slice, it may be more convenient to make the gauge slice a bit fuzzy. Okay, it's just technical trick. Okay, and you see, here in the lambda f of A contains an epsilon. F of A is d mu A. F of A is d mu A minus epsilon. So this is taken care of by ghosts. So we end up in the functional integral with an exponential of, roughly speaking, I lambda epsilon, independent of A. You see here, lambda epsilon in the path integral. And if I integrate over epsilon, and you integrate over lambda, so now if you integrate both over epsilon and over A, oh no, yeah, there was an, I'm sorry, no, there was an epsilon times, the gauge condition was epsilon, the gauge condition was exponential minus, so it was exponential I times lambda times d mu A minus epsilon. Okay. And now if you integrate both over lambda and epsilon, what you get is an exponential of I times minus 1 over 2 psi times d mu A mu squared integrated over x. So this just modifies this is a term that has to be added to the Yang-Mills action. So the final action is S Young-Mills of A plus S ghosts of C, C bar, and A, plus this little additional term, let's call it S psi of A, which come from the gauge fixing. Where S psi is just this object. S psi of A is minus 1/2 integral of d mu A mu squared. Okay? Yes?
Okay, so what exactly is the technical trick that we're doing here? Because I mean, there's a function epsilon which is fixed. And so
Yes.
we're integrating
Yes.
over that.
No. Okay. But
Integrate over something which is fixed.
it's because this integral is basically 1. It's a Gaussian integral, so it's a constant. So I'm just writing that Z now is an integral over dA, an integral over C and C bar. The determinant.
But that integral is not 1 because there's an epsilon in there, and you're integrating over that thing which is also epsilon dependent.
No, I integrate over epsilon, so this doesn't depend on epsilon.
Okay, you have an f of x, and you say the integral of the delta function in x is 0, is 1. So I just add that. So f of x is f of 0. That's what you're doing.
Let me write this. The measure now is integral over dA, integral, oh no, I'm not writing over dc. The measure is integral over dA. Let's keep just the determinant of G of A, not writing it in terms of fermions. And then I have a delta of dF minus, I'm sorry, I have a delta of the F associated to the Lorentz gauge minus epsilon. So I get an I get an exponential of I lambda d mu A minus epsilon. Okay? And I know this is independent of epsilon. That's because I wrote the delta function. I wrote the delta function in terms of lambda. Or if you prefer, do not think about the lambda and just think. Okay. Okay. Let me just write the delta function of f of A. And f of A is f Lorentz minus epsilon. Okay? But I know that this is independent of epsilon. Okay? So I can rewrite this as epsilon is the gauge fixing parameter. No, epsilon is the choice of gauge. Choice of gauge.
Epsilon is just Lorentz.
This is a choice of gauge. Choosing different epsilon means different gauge. And we know the result is independent of the gauge. Therefore, it's independent of epsilon. You see? So I can, without any change, add here integral, I'm going to write this formally, integral over epsilon exponential of minus epsilon squared. Well, normalized, the measure is normalized so that this is 1. Okay, so I add this. Okay, now I interchange this integral over epsilon and the integral over a. And now I have somewhere here an integral which is integral over d epsilon exponential minus epsilon squared times delta of f Lorentz minus epsilon. Okay? And this is obviously exponential of minus f Lorentz squared. This is a trivial integration. But f Lorentz is just d mu a mu. So this means integral over dx d mu a mu of x squared. You see?
Wait, where does the integral come from?
No, it's because when you write this, you must take into account the fact that this is a product for each x. So this is a compact notation. Compact notations. And notation with the x and the a's, this is going to be integral over dx, sum over a of d mu a mu of x, of a and d mu, d nu, if you want, a nu a of x. Okay. So I'm using the compact notation in terms of...
That epsilon squared there is actually an integral over epsilon.
Yeah, so with this non-compact notation, epsilon squared means integral dx epsilon a of x, epsilon a of x. Okay? Okay, so I don't want to spend too much time. That's just a trick, I think, due to Feynman, which makes calculation, which makes the propagator simpler, simply. But you can do the calculation not using this trick, taking just the Lorentz gauge and everything. But, okay. So with this, gauge fixing condition, gauge fixing. Okay. Now, the gauge action is S Young-Mills of A plus S psi of A. S chi of A. Okay. And which means that, so remember, S Young-Mills of A contains a term. Okay?
That integral is 1.
Yeah.
So psi is fixed.
You can try. No, psi is fixed.
Psi is just a number.
It's fixed. It can be anything.
No, it can't just be anything.
No.
That integral is going to depend on psi. So it being 1 fixes
No.
psi.
This integral, well, if you normalize the measure, it doesn't change of psi. It just factor out. Now, the point is that psi is fixed. So, in fact, it is a gauge fixing parameter.
If you divide your exponential by say 2, then you're going to get a different value for the integral.
No, the point is that do you get different values for the? Let me finish my sentence. The question is that psi is another gauge fixing parameter. And therefore, the important point is that do physical quantities, amplitudes, on-shell amplitudes, for physical modes depend on psi, and they do not.
I'm not even talking about physics. I'm just talking about an integral. There's an integral there with a parameter, and hence the integral, the value of the integral depends on psi. And you want to fix it to be 1.
No, I don't want to fix it to be 1. Here I fix to be 1
That equals 1.
Here I fix to be 1 to illustrate the calculation. But if I do not fix it to be 1, then you get psi here. Okay, let me continue, and you'll see that it's not a problem. So psi is a gauge fixing parameter. So the important point is that do the physical quantities depend on the gauge fixing parameter? And no, the question is it. Okay, so the Yang-Mills action is now this for this plus this, okay?
We started the lecture with a certain action, and you kept adapting it, but it's not equalities. You just kept taking a new action.
No.
We keep adding parameters and changing the action.
The point is that does this action depend on this parameter? And in the same way that this doesn't depend on the choice of f.
You're just multiplying it by a function depending on epsilon.
Yes, but this function doesn't depend on a.
So?
This is independent of a.
You multiplied your entire action by a constant.
I cannot multiply the action by a constant. I can multiply the functional integral by a constant. Because it cancels between the numerator and the denominator when you compute correlation expectation value of operators.
Only taking different actions. There's no equality in the entire thing here.
No, the equality
We're
is
not
that
writing anything.
the equality is going to be that when you compute vacuum expectation value of operators O1, On, which are gauge invariant, or through LSZ reduction relation, when you compute scattering amplitudes between gauge field configuration, which is gauge modes, with a transverse mode, such that the polarization, well, it's a different epsilon, such that if you have a polarization vector E, such that E dot K is equal to 0, with K squared equals 0, so it's on mass shell. So on shell, this should be, both this and this should be independent of f, the choice of gauge fixing, or using a trick of Feynman, or of f in particular of my parameter psi. That's all what we want. Okay. Okay, so now let's go back to this. So remember what was the action for? So f psi of A is just a d mu a mu squared. S Yang-Mills, remember, was one over 2g times trace integral over d4x trace of f mu nu which amounts to be, let me go back to the, yes? No, I wrote already the ghost action. Now I'm writing the action that do not involve ghosts, but which is pure gauge fiction. The action involving only the gauge field is this. And let me just write a mu. So it's trace of f mu nu. So in terms of with f mu nu, this is d mu a nu minus d nu a mu, and plus or minus I the commutator of A mu and A nu. And remember, this in this writing, A is an element of the adjoint representation, so it's a 2 by 2 traceless matrix. So in terms of component of A mu, A nu, it involves coupling with the epsilon A, B, C. Okay. And let's rewrite it. S psi of A is just integral over dx, well, 1 over psi, 1 over 2 psi, d mu, a mu, d nu, a nu. Okay. Good. Okay. So, S Young-Mills contains a quadratic part. It contains a quadratic part. Let's say 2 plus S3 plus S4. Okay. And the quadratic part is just of the form some A mu times some differential operator, something that I called, I think, K mu nu or D mu nu, I don't remember. D mu nu, and now this is going to be D mu nu, the original D mu nu of Maxwell, let's say, basically, of Maxwell theory, plus this additional term, which is 1 over psi, well, S Young-Mills plus psi, plus 1 over psi times d mu d nu up to a sign minus, well, there is a factor of 1, 2 in front. So this is this times A nu. Okay. And remember, d mu nu was basically, if I'm not mistaken, was d mu d nu minus delta mu nu, the ordinary Laplacian. And it had 0 modes. So in Fourier space, d hat mu nu is minus k mu k nu plus delta mu nu k squared. And it has 0 modes since k mu d mu nu equals 0 for any k. Now with this gauge fixing term, this becomes a factor minus 1 over psi, well, plus 1 over psi k mu k nu that you have to add to this. And this, of course, when you add the k mu, this is different from 0. So this term removes the 0 mode associated to gauge fixing longitudinal mode. So it does the job. So this means that it does the job. What required for gauge fixing? We remove the problem associated to the 0 mode. Okay. And so with this notation, what are the Feynman rules for the gauge field? So first, we have a propagator. We have so now what are the, well, maybe I should, this is the action. Let me go one more and just, well. Now what are the Feynman rules for the gauge fields? For the gauge field. Okay. First, we have a propagator. that I'm going to represent like for Maxwell theory for QED. And now the propagator is just, well, the inverse of the form D minus this. So you do a bit of algebra, and you find that this propagator, so this propagator, of course, A mu carry a Lorentz index, and it carries a color index, A and B going from 1 to 3, because now there are 3 gauge fields. So this propagator is a function of the momenta that flows through the propagator, but it's a matrix with index mu nu and index AB. So it's a 4 by 3, 12 times 4 by 3 matrix. Okay. Okay. So the color index matrix is very simple because the charge is conserved. So there is a delta AB. Okay. Okay. Now we expect to have the propagator of the standard Maxwell theory. So we expect to have a 1 over k squared, and since I am in Minkowski space, there is a minus I over k squared minus I epsilon. This is the Feynman propagator. And there is a mu nu part, and the mu nu part is going to be h mu nu plus chi minus 1 times k nu divided by k squared. Okay, so this is a propagator of the gauge field. Okay. Is it okay? Pardon?
Epsilon plus?
Epsilon plus is just, you know, the Feynman prescription.
Ah, okay.
Just, to go around the poles. It's just a prescription that gives the Feynman propagator and not the advanced or retard propagator. Well, there was a lot of epsilon, so if you prefer, let's write it 0 plus. This means that it's some small positive number that goes to 0. Okay. And I think that, for instance, if you take psi equal 1, this disappears, you get something like that. So I think that's, in fact, up to the delta AB, that's the propagator of the fermion you got in QED. Okay. 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 And you see that if you consider in particular, if you consider the propagation of a transverse mode, a physical mode with a polarization epsilon. So I assume that A mu of k is just of the form epsilon mu with epsilon mu k mu equals 0. So that polarization of the electromagnetic field is transverse to the momenta, then you can check that when you take this propagator and you consider the propagation, you can check easily that epsilon mu times this propagator, let's call it G mu nu of k, is just epsilon mu h mu nu. So this is just minus I over k squared epsilon nu, and it doesn't depend on the gauge fixing parameter k. So the propagator of the physical mode of transverse polarization do not depend on the gauge fixing procedure used. Okay, I'm sorry, this is a bit slow. Okay. And that's so. And this part is just QED. So all what I did here, I could have done it for QED. And you probably did it in some way or some other in QED. Okay. So now the difference between Maxwell's theory and non-abelian gauge series, of course, comes from the fact that we have a coupling between, so this is 4, 5, 6. So now, of course, we have to consider that we have a couplings between the gauge field. Okay? Because we have F mu nu contains D mu, and then A and A. So you may have a term involving 3 bosons, which is of the form of the general form dA times A times A, with a lot of indices. So it's written in the note. You could I could write it in the, but basically, the point is that this corresponds to having a 3 gauge field interaction vertex with a d mu, which means that this vertex depends on the momentum carried by one vertex. So it's going to, this vertex is going to depend on the momentum k carried by the vertices. And it's going to be proportional to the coupling constant. Because when we do perturbation theory, we rescale A by square root by G. Okay. So it's proportional to the coupling constant, and it involves a constant. And it involves of the momenta. Okay. And well, if you are very careful, you can, but you can find the details, for instance, in the book by Peskin and Schroeder. Of course, this is going to depend on the Lorentz indices mu, nu, and rho. So those are indices for the polarization of the field, and the color indices A, B, C. Okay. And it depends on the momenta. Let's write this like this is the momentum K. This is the momentum P. And this is the momentum Q. Of course, you have conservation of the momenta. So you have P plus Q, K plus P plus Q equals 0. These are 4 momenta. And if you walk out a little bit, let me write it. I'm not going to write it for the 4 vertex, but this is epsilon ABC h mu nu k minus pi rho plus the two other terms that you can write by making a permutation of the ordering of the vertices. Okay. So you start from this, where you see you isolate those two, you take k, this one, the first one, minus the second one, momenta, and you multiply by h mu and h nu. And you take a component, the rho component of k minus p. And then you take the second and the third, so that it's symmetrized. Okay, so this is a vertex. This is a 2 gauge field, a 3 gauge field vertex. Okay. And then you have an S4 terms involving just the products of the two commutators. So it's going to involve A, and A terms, so it will be a 4 gauge field vertex. And it's going to be like this. It doesn't depend on the momenta since there are no derivatives. Okay. It's proportional to k squared, to g squared. I'm sorry, it's because it involves more coupling constant. But of course, it depends on the momenta A, mu, B, nu, C, rho, and D, sigma. So it depends both of the polarization indices, Lorentz indices, and the color indices. And it's a bit complicated, but it's going to involve some epsilon A, B, C. So let me write, well, okay, it's going something like this. It's epsilon A, B, C, epsilon A, epsilon C, D. Well, where is there an E? Oh, no, it's because it's a product of two epsilon. It's a product of two structure constants, and then you have some H. You have H mu rho H nu sigma minus H mu sigma H nu rho, and then you have 3 different contributions corresponding to the 3 channels of this 4 particle vertex, because you see this is a channel where mu and rho play a role, and nu, or mu, no, so you have mu, no, so let's say epsilon AB plays a difference at CD. So in fact, it's a channel where you have this going to this. So this is something like the S channel, where you consider this going to this, and if you consider this AD going to BC or AC going to BD, you are going to get 2 different contributions. S U T U, okay. Okay, so you have this vertex, this gauge fixed vertex, and the important point is that, of course, the gauge boson exchange is an exchange of charge. Because since you have some epsilon ABC here and some double epsilon AB and CD, it means, for instance, that if you have a boson with a color 1 and a boson with color 2, they interact, and what's contributed is a boson with color 3. And here, similarly, in fact, this can be rewritten as a product of delta function, which means that they can exchange color. So there is color exchange and transmutation of charges. So this process do not conserve. Well, okay. And so the dynamics is quite complicated, even at the level of perturbation theory. You have a propagation of a gauge field which is basically the same than for if it was photons. They are charged, but the charge is conserved. But then you have the interaction vertex with three and four particle vertices, which makes the theory much, much more complicated. Okay, and since I have only, 3 minutes left, let me just go back to the coupling with matter. That I've not really discussed. So let me go back and just assume that the theory is coupled with Dirac fermions. Or it could be the quarks, for instance. Okay. Well, the quarks are, well, it's more complicated because you have a list. And so for the, where is it written here? Well, I discussed that a bit later. So remember, so we assume that we have Dirac fermions, so we have fields, we have psi and psi bar, which are Dirac fields, but they belong to the fundamental representation. So for SU2, it means that the carry index, so psi means psi alpha I of x, where I goes from 1 to 2. This is an index of a fundamental representation of SU2. And the alpha going from 1 to 4 are just the standard Dirac indices, since the field is a spinor. Okay? And the action S for the fermions, we just take it to be the standard Dirac action. Where is it written? Yeah. Which is integral over dx psi bar I d slash minus m psi. And now, well, it's exactly like in QED. In order to have a gauge invariant theory, d slash, well, d slash is gamma mu d mu, with d mu the covariant derivative that I have defined on Tuesday. Okay. Oh, that's good. Define it on Tuesday. But acting on the fundamental representation. So d mu is just the ordinary derivative minus I times a mu. Where was it written in my notes? Covariant derivative, yes. Oh, d mu is just ordinary derivative d mu minus I times a mu. So I remember, covariant derivative, in the covariant derivative, psi is a vector with two components, and a mu is a 2 by 2 matrix, so it transforms, acting on psi, it transforms a vector, a 2 vector into a 2 vectors. So that's the standard action on the fundamental representation. Okay? And therefore, in terms of components, well, you have the ordinary. You see, you have just the ordinary. So for a fermion propagator, that goes from psi to psi bar. Okay, it's just now they transform. They carry an index alpha and an index I, and then index beta and an index G, and the Feynman propagator. The fermion propagator is just the standard propagator. It's 1 over p slash minus or plus m, I don't remember, but that's not important. So it's a standard propagator for fermions. Plus I epsilon with a factor I probably, because it's a matrix alpha beta, times the delta Ig, because the charge is conserved. Okay? And here you have a vertex of interaction between the gauge potential and the fermions, which is the same than for electromagnetism, except that the gauge field now contains an index of charge in the fundament in the adjoint representation. So this is going to be the standard vertex here of there is going to be a factor G. Okay. Beta. There is going to be a gamma matrix. Oh, and it carries an index mu. So there is a standard gamma mu alpha beta matrix term of the, like in QED. Okay. But now there is a term that involves the coupling between the charges, and this is going to be, of course, simply the matrix element Ig of the generator A of the Lie algebra. And for SU2, remember, TA is just 1/2 of sigma A, where sigma A is a Pauli matrix. And therefore, here again, there are exchange of charges between bosons and fermions. And that's something which is new with respect to QED, because in QED there is only one index 1, which means that the photon is neutral, and therefore the charge of the incoming particle is the charge of the outgoing particle. Here, the charge is more complicated. That belongs to the representation, non-trivial representation of the gauge group, and therefore the charges mixes. Okay, so let me end there. And tomorrow, last lecture, I'm going to discuss, I hope, a bit of physics, but first I'll give you an outline of renormalization theory. Okay, thank you.